We're now going to work a second example problem involving an air conditioning process. And with this one, it will be at 1 atmospheric pressure, and consequently we'll be able to use a psychrometric chart. And what it will do is it will demonstrate how useful this chart is, because it enables you to do the calculations much quicker than what we saw in the previous problem where you have to evaluate all the different property values and terms. So what I'll do, I'll begin by writing out the problem statement, and then we'll start working the problem. So there's our problem statement, what we're dealing with, an evaporative cooler. Remember, this is an air conditioning system for cooling that you would use in very dry climates, desert-like climates. And we're dealing with air at 1 atmosphere, 36 degrees C coming in, so that's quite hot. However, if you notice the relative humidity, 20%, that's very, very low, so it's quite dry. We're told that it's coming in at 10 meters cubed per minute, that is the air. And it's leaving at 90% relative humidity. So we're adding a lot of moisture to the air. And what we want to do is we want to find the exit temperature, because that would be the then temperature of the air leaving that you're using for your air conditioning process, as well as how much water we need to constantly add to this system. So that is the example or the problem statement. And what we'll do, we'll begin by writing out, drawing a schematic of the problem. So we'll do our common duct. And we have state 1 here. And remember, I said evaporative coolers could be different types of configurations. It could be spray. This could be a porous media that the air is flowing through. One that ideally doesn't have too much of a pressure drop, but in the process, water droplets are being entrained into the airflow, and as they evaporate, they cool. So what we know is we know that we have 1 atmosphere pressure for the air coming in, 36 degrees Celsius. We're told the relative humidity at 1 is 20%. And we have the air flowing through, and then when it's leaving at state 2, we don't know the temperature, but we are told the relative humidity goes up to 90%. And so we have mass flow rate of water coming in here. We do not know how much. And so that is, let me just try to clean that up a bit. Mass water in. So those are the things that we know, what we're trying to find. First of all, we want to find T2. We want to know what the temperature leaving is. And then we want to know mass water in, how much water we need to replenish this system with. So what we're going to do, we're going to be able to solve this one using the psychrometric chart. And recall, whenever we were talking about evaporative cooler, we did say that the enthalpy of this process was constant. So H1 is equal to H2. So we have an evaporative cooler. So those of you who live in the desert, you will know what these systems are and how they work. For those that are in humid climates, you probably haven't seen these and you wonder why anybody would want to add humidity to the air in order to cool. Well, it works very well in dry climates. So anyways, what we have there, H1 equals H2. So what I'm going to do, I'm going to begin by writing out, we have T1 equals, that's going to be our dry bulb temperature at point 1, and that is equal to 36 degrees C. And we have the relative humidity there is 20%. So what we're going to do, we're going to take these and we're going to go to our psychrometric chart and we're going to try to read off some of the values from that. So let's take a look at our psychrometric chart. Remember, we have 36 degrees C and 20%. So here is the psychrometric chart. And what I'm going to do is I'm going to write this in red so that we can see it. So we're going in at 36 degrees C, so 36. And we're told 20%. So what we do is we go up vertically until we intersect with the relative humidity line at 20%, which is right there. I'll circle that in blue so it's a little easier to see. So that is state 1 in our process. Now what I'm going to do is I'm going to strip off a couple of values here. I'm going to take off the, first of all, the specific volume of the air, and specific volume are the red lines that run up and to the left. So we have one specific volume, and I'll use, let's see what color. We have all different colors on here, so I'll go back to black. We have 0.88 and then we have 0.90. And what we can see is that we're kind of halfway between 0.88 and 0.89. So we're probably somewhere around 0.885, 0.886. So that will be the first thing. I'll say V1 is 0.886. And the other value that I want to strip off here is going to be, and I'll do this in red again, the specific humidity. So I'm going to move over to the right hand side, and you can see we're coming in just right below 8. So we have 6 here, that would be 7. So we're probably right around 7.5. So specific humidity at 1 is 0.0075. So we have those two. And what we'll do, let's return back to our problem. So we have specific volume at 1, 0.886, and that's meters cubed per kilogram. And then we have specific volume at 1, 0.0075. And I'm going to use those in order to determine the mass flow rate of dry air coming through our system. And so if I look at the volumetric flow rate coming in, we're told that it was 10 meters cubed per minute, which translates into 0.1667 meters cubed per second. And from that, we can determine mass flow rate of dry air and that is going to be kilograms per second. So that's one thing we have. Now, another thing, we can determine the mass flow rate of water at state 1. So that's the mass flow rate of water entering, knowing the specific humidity at 0.1 and the mass flow rate of dry air there. And we get that to be 0.00141 kilograms per second. So that's another piece of information that we have. What I want to do is go back to the psychrometric chart and pull off the value of the enthalpy. So let's take a look at enthalpy here. And for enthalpy, recall, I'll use a green. I'll use red because green might be hard to see. But enthalpy are the green lines moving up and kind of to the left. But our state is here, and we're going from there up to 90% humidity. And so the enthalpy in this process is not changing, but I would read the enthalpy here to be partway between 50 and 60. So it's probably, it's a little bit beyond the halfway point, so maybe 56 kilojoules per kilogram of dry air. So what I would say here is H1 equals 56 kilojoules per kilogram dry air. And the way that I was able to get that, I move up here and we get something that's right in about there. So that's where I'm pulling that 56 from. So let's go back. And what we can say is H1 is 56 kilojoules per kilogram dry air. H2 for an evaporative cooler is approximately H1 and 56. We know the relative humidity at 2, we were told was 90%. So from this, I'm going to go back to the chart and we can now pull off state 2 information. So let's go back to our chart. And if we follow up the constant enthalpy line, and I will do this in red, we go up and we get to our 90% point. We're probably right in there. Oops, sorry about that. We're right in here somewhere. So that would be our state. And then I'm going to draw a blue circle around that. So that would be state 2. And now what I'm going to do is strip off our different temperatures. And so to begin with, the dry bulb temperature, for that I'm going to come straight down. And I get a value right around there, which I would say is about 20.5 degrees C. So with that, temperature dry bulb 2 equals 20.5 degrees C. And the other thing we want to find out is we wanted to determine the amount of water being added. So I'm going to pull off specific humidity at state 2. So for that, what we do is we go directly over to the right. We come over here and we get 14. So I would say omega 2, it might be a little bit below, looking at where it is on the graph. So maybe a little tiny bit below 14. 0.01375. So I'm going to take those values now back to our problem. And what we have is T, let me write that in black. Temperature dry bulb at 2, which is actually the temperature coming out, is 20.5 degrees C. So you can see that is the cooling that we've achieved. We've gone from 36 degrees Celsius down to 20.5, which is really a considerable cooling. And the specific humidity, 0.01375. So if you can handle the increased relative humidity and it doesn't make it uncomfortable for you, the cooling is definitely going to make you happy in this climate that's at 36 degrees C. Last thing we want to do, we want to find out how much water we need to add to the swamp cooler to make it work, or the evaporative cooler. So water balance. And for the water balance, what we can do, we have water at 1 plus mass flow rate of water being injected is equal to mass flow rate of water at 2. And we can make our substitutions using the dry air and the specific enthalpy flow rates. Or sorry, the specific humidity. Okay, so we get that. I'm going to isolate for mass flow rate in because that's what we're looking for. So we have this equation here, and if you notice, we have everything for this equation. We know the mass flow rate of the air, we know omega 2, we know omega 1, so we can calculate everything. And from that, we get mass flow rate of water in. And expressing this in kilograms per minute. So that's the amount of water that we would need to add to this system in order to drop the temperature from 36 degrees C down to, what did we say, 20.5, but the humidity, relative humidity is going from 20% up to 90%. So that gives you an example of using the psychrometric chart. You can see the psychrometric chart is relatively simple and straightforward to use. It's a little busy, but as long as you know the different things on there, it's quite easy to navigate. You might want to use a ruler in order to get a more accurate measure than I had here. But nonetheless, a pretty quick way of doing these calculations versus the last problem that we had, where the calculations were a lot more involved and took a lot longer. So that concludes the lecture as well as the section on heating, ventilation, and air conditioning. I'd like to thank you for your time.